Hello there. So let's go ahead and do this problem. This is a problem related to stability of beams or static equilibrium, systems in static equilibrium. Okay, so it's called static equilibrium. So if a system or an object is in static equilibrium, there are two conditions that the object or the system is going to satisfy. The first one is called translational equilibrium. And that means the net force acting on the system or the object is equal to zero. Okay. The second one is rotational equilibrium. It's called rotational equilibrium. And that's the net torque about any point on that system or the object that's equal to zero. So that's what we call static equilibrium. It's just these two conditions. So let's go ahead and read the question. So here there's a 20 kilogram board, 4 meters long, and it's a uniform board. It is supported at each end. Okay. A 70 kilogram person stands 1 meter from the left end, and the system is in static equilibrium. As you can see here, is the board is in static equilibrium. So the extended object is shown, and the forces acting on the extended object are also shown. So there's a force in the upward direction at the left end of the board, and then there's a force on the right end acting on the board. You can see F of R. And those are the two values that we need to find out, the two forces that we need to find out. Then there's the weight of the person acting vertically down, big mg, and then the weight of the board, which is acting through its center of mass, because it's going to be a uniform board. So that's mg. Okay, so let's try to solve this problem. So first, I'm going to use translational equilibrium. Looking at the stability of the board, I'm going to write down the net force equals zero for the board. I'm not looking at the person. I'm looking at the stability of the board. The net force is equal to zero. So that's one condition that needs to be satisfied since the board is in static equilibrium. So let's consider, since we are dealing with forces, that's a vector quantity. So let's consider upward direction as the positive direction. So that's our positive direction. So then you can see from the forces acting on the extended object, I have F of L upward minus the weight of the person minus the weight of the board plus F of R. Okay, so that's my first equation, and this entire, so this net force is equal to zero, and I can consider this as my first equation. So we got one equation, and then I'm going to look at rotational equilibrium. Because again, the system is in static equilibrium, rotational equilibrium must be satisfied, and that means at any point on the beam, the net torque is going to be zero. So here, what I'm going to do is that I'm going to consider the net torque about point O. You can see point O. Why? Why am I doing that? Because you can see one of the unknown forces, F of L, its line of action is going to go through that pivot point. So then there's no torque acting on the extended object, that is the beam, due to that force. So when I write an equation for the net torque on the beam, I won't get any contribution from that unknown force F of L. So that's the main reason I'm going to strategically use that point O to figure out the net force acting on the beam. Okay, so keep that in mind. So again, for the board, the stability of the board, I'm going to consider the net torques about point O. And that needs to be 0. And here, as you know, traditionally, counterclockwise torques are considered positive and clockwise torques are considered negative. So I'm going to consider counterclockwise torques are positive. Okay, so if we consider point O, you can see, force F of L goes through that point, so there's no torque caused by that force. Look at mg, the weight of the person. That's going to cause a clockwise torque. So that means I need to consider a negative sign because it's clockwise, right? I'm considering counterclockwise as positive, then clockwise torques will be negative. So that's why I'm going to put a negative sign. Mg times the distance, the shortest distance between point O and the line of action of mg. What is that distance? That's, you can see that's x1. So I'm going to multiply that with x1. So that's how you find the torque. Force times the shortest distance from the pivot point, or the point where we consider the torques, and the line of action of the force. Again, how do you find the torque? Multiply the force by the shortest distance between the pivot point and the line of action of that force. That's what I have done here. And then I'm going to the next force, which is the weight of the beam. Again, that's going to cause a clockwise torque about point O. So that's why I'm going to again put a negative sign. So this time it's going to be lowercase mg times x2. And then look at the torque caused by that unknown force acting at the right-hand corner of the beam. So that's going to cause a positive torque. Okay, that's going to cause a positive torque. So I'm going to put plus f of r, and then the distance, you can see that's going to be x3. That's going to be x3. And this is the net torque acting on the beam, which is equal to 0 since the system is in static equilibrium. And now we can solve for the unknown. So this is algebra. So and then we can actually call this equation number 2. Now look, we have two equations and two unknowns, where the unknowns are f of L and f of R. So we can solve this problem. So what I'm going to do is I'm going to look at equation number 2 and solve for f of R. So from 2, I'm going to solve for f of r. You will see I'm going to keep all these algebraic like terms, as is. And then when I get a nice expression, that's where I'm going to substitute the numerical value. So this is basic algebra that you need to know. So I'm going to take this first term and the second term to the right hand side, so they become positive. So I have big mg x1 plus small mg x2, and then the entire thing should be divided by x3, right? So that's what I'm going to do, x3, divide that by x3, and then you can see g, which is the acceleration due to gravity. So I'm going to just factor that out. So mx1 plus mx2, and then factor out g, divide this by x3. Now I'm ready to substitute the values. Okay, now I'm ready to substitute the values. So a big M, as you can see, let's go back to the problem. Big M is 70 kilograms, the mass of the person. times the distance x1 is just 1 meter, plus small m is 20 kilograms, and x2 is 2 meters. Okay, and then G is 9.8. You just put the magnitude of that value. Okay, you're not going to put a negative sign. It's just the magnitude 9.8. Why? Because the weights are pointing downward, right? So we already have considered it's pointing downward. So that's why I'm just going to put the magnitude of 9.8, not with the sign negative 9.8. So keep that in mind. We are just putting the magnitude of G, 9.8, and then divided by the x3, which is 4, And then you can go ahead and simplify this 70, and there's a 40 here. So 70 plus 40, that's 110. 110 multiplied by 9.8. And then this entire thing is divided by 4, which is going to be 1078. You can use a calculator, divide that by 4, and then f of r is going to be 269.5. And what's the units? What do you think the units? This is a force, right? So the SI unit for force is newtons. And then you can see this is a positive value, and that makes sense because we considered upward as the positive direction, and the force acting on the right-hand side, it's in the upward direction. So that's correct. So this is positive, and that's one of our answers, f of r. Now, how do we find the force acting on the left end? I'm going to use equation number 1. From equation number 1, I'm going to solve for f of L. You can see simply I'm going to push all these 3 terms. You can see these 3 terms to the right-hand side, to the other side from the equation, equal sign, and then I get this expression, m big mg plus small mg, and then a minus f of r. And if you like, you can further simplify. You can pull out that g term minus f of r, and then go ahead and substitute. So 70 plus 20 multiplied again by 9.8. Don't put a negative sign, okay? Because again, we have considered that the weight is pointing downward. So that's why in that figure, you have the arrows, the vectors, the weight vectors pointing downward. So there's no need for us to put a negative sign there. Minus f of r, which is 269.5. And then you can go ahead and simplify. So this is going to be 90 times 9.8 minus 269.5. And then your answer is going to be 612.5 newtons. Again, that's a positive value, and which makes sense because both forces at the end of the beam, they're pointing upward, and we considered up as the positive direction. So that's how you do this problem. So the unknown forces acting on the beam on the left-hand end, it's 612.5 newtons, and on the right-hand end, that's 269.5 newtons. So that's how you do this problem. This is the way you do this problem. So I hope you enjoyed my explanation. So if you like this video, hit the like button, write down a comment. If you need more videos like this, just comment, and I'll be more than happy to share my techniques, my knowledge with you guys, my community. Okay, then see you with the next video very soon. Bye now.